Hello and welcome back to another LeetCode problem. Today we're going to be doing the problem of the day of June 11th, snapshot array. And so it says implement a snapshot array that supports the following interface. We can initialize an array like data structure. Initially every element equals 0. We can set the element at a given index to equal val. We can snap, that takes a snapshot of the array and returns a snap ID, which is the total number of times we called snap -1. And then getIndex returns the value at given index at the time we took the snapshot with snap ID. And so let's take a look at the example. So here we have an array. Let's just draw this out. So we have an array of length 3. And we make it. We set array 0 equals to 5. Then we take a snapshot at ID 0. So this is what the array looks like at ID 0. Let's just say that. Then we set this equal to 6, so we'll draw this down here. So this 5 becomes a 6, and these are both 0. And then we want the snapshot at ID 0 of this index. So that's going to be 5. So how can we do this problem? Like, basically what it's saying is at every snapshot we have to capture all of the elements in the array and we have to save that. But the problem is, if you look at these constraints, the length of the array can be 10 to the 4th, and you can also have 10 to the 4th calls. And so it's actually 5 times 10 to the 4th. So worst case scenario, imagine you just take like 5 times 10 to the 4th snapshots. If you just store the array with every snapshot, that would be 5 times 10 to the 4th times 5 times 10 to the 4th storage. And so that's going to be really problematic, right? That's 10 to the 9th, and that's a big value. So this is a quadratic solution. And let's think of this storage would be really big, but on the bright side are, we'd have O of 1, time for get, but the problem is our storage is n squared. So how can we try to compromise between our storage and our time to make a more efficient solution? And so if you think about it, let's just think about we have an array, right? Let's just say we have an array like this. And all we're doing is taking snapshots, right? So we take a snap, 0, 1, 2, 3, 4, 5, 6. And so every time we take a snapshot with our old solution, we would have to store the entire array at all of these, right? So at 0, it would be 5, 0, 0. At 1, it would be 5, and so on. But we didn't actually change anything. So this is really inefficient, and let's just think of how we could do this better. And the key thing is, we don't really need to return the value of like every single value, and also when we set, we're only changing one value. So if we're only changing one value, why would we store the entire array every time? Like, if we only change one value, the other numbers stay the same. So let's think of a way how to do this better. And so what we're actually going to do here is, instead of storing the entire array at every single time that we take a snapshot, instead we are going to, every time we change the value, we are going to not only change the value, but we're also going to record what was the snap ID that we stored it at. And so let's say we want to change this like 5 at index 0, or store it at index 0, and we want to change this to a 6. We're going to say, okay, we're going to store the snap ID at the current time. So like in this example, when we change this 5 to a 6, our snap ID would be 1, because our snap ID starts at 0, so it'd be 1. So we would store something like 1 and then 6. And then we're gonna store this in some dictionary with keys being the indices. So this is gonna be index 0, and then we're gonna store like this 1, 6. And so let's take a look at what this would look like for that example, actually. So in the beginning, what we're gonna do is we're gonna store so we're gonna have this D. We're gonna store at every index. It's gonna be snap ID 0 and value 0, because the initial values are zeros. So we're gonna have index 0, index 1, index 2. And we are going to store, remember, we're going to store, it's going to be, the whole thing is going to be a list. And it's going to be like this. And now we are going to store snap ID and the value. So that's 0, 0 initially for everything, because the snap ID is 0 and the value is 0 for everything. So that's 0, 0, 0, 0, 0, 0. Okay. Now we take a snapshot, so we update our snap ID. So let's just say ID. That's gonna be 1 now. If we took a snapshot, we returned 0. Now we're gonna update it to a 1. Now what we want to do is we want to change the value at 0 to a 6. So we're going to go to index 0, and we're going to say, okay, what's our current snap ID? It's 1. And now we want our value to be a 6. Or actually, so I did forget one thing, by the way. So, yeah, I did. Okay, so wait, I didn't do this set 0, 5 thing. So we want to set this 0, 5 when our snap ID is still 0. And in which case, what we're going to actually do is when we try to set an ID, we're going to go into whatever the list at the index we're at, and we're going to look at what's the last ID in there. And if that last ID has the same snap ID as the index we're currently at, we're just going to replace the value, but keep this, right? Because we are still at the same snap ID that is the last one. And so we are going to want to change this value to a 5. And what we're going to do in our implementation is we're going to pop out this whole thing, and then we're going to replace it with a 0, 5. Because we have the same snap ID as we had before. So for example, like let's say we just call a bunch of sets like 0, 5, 0, 6, whatever, at the same snap ID, we're just going to want to replace the value there. But as soon as we go to a different snap ID, we can no longer replace the values because now they're different states. So yeah, so we're going to have the 0, 5. We're going to do this ID 1. Now we have a 0, 6, but our ID is 1, so we can no longer just get rid of this because we have a new snap ID. So now this is going to be snap ID 1, 6. And then when we want to get the value with snap ID 0, how would we do this, right? So we're going to have a list at every single index of an array of the snap ID and the value. And so we can, because they're going to be sorted, they're always going to be sorted, right? Because snap IDs are always going to be increasing. How do we get a value really quickly in a list, in a sorted list? We've done this a lot, right? It's going to be a binary search. So we're going to binary search in here and find the index that's closest to the snap ID, but it has to be below the snap ID, and that's the value we're going to return. So in this case, we do have an exact index that we're trying to get, right, for the 0, 5. So we do have the 0, 5, then we would just return this 5 value. But for example, let's say that we continue on with this thing, and then let's say we take another snapshot here. We update our ID to 2, and then we insert something. So let's say we insert something here, like we insert 3 at, sorry, this would be ID 2, right? So this would be ID 2, we insert 3, and then let's say we insert something here. So let's say we insert 4. This would be ID 2 as well. So ID 2, insert 4. And now let's say we are called snap ID where we want to call snap 2 at index 0, right? So the thing is, we're going to go into the 0 again, and we're going to try to find a 2, but we're not going to find a 2 because we never actually update anything to be the snap 2, but the value we need is the value closest to 2, and it needs to be below 2 because that's the last time that we updated our value. So we just look for the last time that we updated our value. So the value, the index we're looking for, so let's call that I, is going to be less than or equal to this snap right here that we are trying to get in this get. So the snap ID needs to be greater than or equal to I. We're just trying to find the closest value here. And so because we don't have a 2, our closest value would be a 1, so we would pop a 6. And that would be our result. So hopefully that makes sense. So we're going to initialize your data structure. We're going to make this dictionary. For set, all we're going to do is we're going to update one value in here, and we're going to check, is the snap ID of that value the same as it was before? If it is, we're going to pop that and replace it because that's the exact same snap ID. We have it, like, what a snap actually means is we can no longer change our array after that snap. It's a whole nother state. But before we've snapped, we can keep changing the value and just update it. And so we can't do that after we snap. We have to do that before we snap at the same value. Okay. And then snap is just literally just going to update the ID. We're not actually going to do anything on snap. We're not going to save the whole array this time. And then get is just going to find the index, binary search to the value closest to snap ID. It has to be, remember, it has to be less than or equal to, ideally equal to, but if there's nothing equal to it, we need to find the value closest to it. And then we're going to get the index closest to it and return the value there. And so that's going to be our algorithm. And let's code it up. So remember, we're going to initialize the data structure first. So we're going to have something like self.items, let's say, equals and this is going to be a dictionary of lists. Then we're going to have a self.snapID. It's going to start off at 0. And what we need to do is we need to actually remember in the beginning we're going to take every single index, and we're going to put in snap ID 0 and value 0 because that's what they all start at. So for I range length, I'm going to append 0, 0 here. Okay. So now we are going to set an index. And so remember, when we set an index, what we need to do is we need to actually go to the items in that index and we need to check, is the last item in there at our current snap ID? If yes, we're going to pop it and replace it. And if it's at a different snap ID, then we just put in our new snap ID in the value because that's a totally different instance and we don't want to replace old snap IDs. Okay, so let's do that. So if self.items index, we want the last value, so -1, and we want the snap index. So remember, it's going to be stored as a pair of snap index comma value. So snap index would be 0 here equals self.snap ID. That means we haven't yet changed the snap ID. Then we're just going to pop. Get rid of that value. And now we can simply insert the new value regardless of whether we popped or not. So self.items index dot append, and remember we're going to append the current snap ID, and we are going to append the value. Okay, so snap is pretty straightforward, so that's just going to be snap ID plus equals 1, and then they actually want you to return the number of times we've called it, which would be this self.snap ID -1. Okay, because like the first time we call it, this value would go from 0 to 1, but we've actually only called it we've called it 1 time, but they want you to return the number of times you called them -1, so they want you to return 0 here. Okay, now get is going to be our complicated function. So what it's going to do is it's going to we need to go through, remember, our array at the index, so let's actually just get that array first. And so let's do that. Get rid of these emails. Okay, so let's just do cur items maybe equals self.items at this index. So this is going to be the list of all the values at different snap indices, or at different snap times for this index. Now we'd have a left and a right, just like we normally do in a binary search. Okay. Now what we want to do is we want to have a res, and we are going to be, the res actually doesn't matter, so that can just be 0 or something, and then we need a res index, and this is the thing that we're going to be maximizing. So remember, we want so this res index is really, I can even call it, maybe this is a better name for it, res ID, and we're trying to maximize this ID, so we want the ID in this list that's closest to snap ID without being greater than it. So it has to be less than or equal to it, and we want the value that's closest. And so if we want the value that's closest, let's just make that -infinity to start, and then we can do that. Okay. Now, so this res doesn't matter because we're always going to find the value that's closest to snap ID. So actually, yeah, these values can't be negative, so we can just make it float -infinity just in case. It's fine. It doesn't really matter, really, because this is guaranteed to be changed. Okay, so while standard binary search. Okay, and now what are the conditions? So if cur items pivot. So actually, I do want to yeah, let's actually get these values, right? So let's just say this is going to be cur ID and cur value, let's say, equals cur items pivot. Yeah, so we're going to get a current ID and a current value. Okay, so now, if cur ID equals snap ID, then that's the exact snap ID we wanted. So then we can just return straight away. We can just return cur val. Okay, and what are the, whoops, I don't know what I'm doing there. Okay, so what are the other cases? So if cur ID is greater than snap ID, that means we want to go left, and we don't want to record this value because it's too big. So that's going to be right equals pivot -1. And now the other case is we are less than snap ID. So for less than snap ID, we actually need to check if res ID is less than cur ID. Remember, we want to try to maximize this snap ID. So if the res ID is less than cur ID, we need to update the res ID and the result. So res ID equals cur ID, and this is res equals cur val. And remember, this is when we were less than the value, right? So we were looking at some indices, and we're less. So like, let's say we're looking for 2 here. We're at some value here. If we're at a value that's less, we want to go right. Okay. So that means if we want to go right, we would do left equals pivot +1. Okay, we can return res here. We were pretty much guaranteed to always run into a value because this is going to be a non-empty array. All right, so let's try this code and see what we screwed up. Okay. Let's see here. Oh, yes. So we are missing this I. Okay, let's see if that's it. Okay, list index out of range. All right. Missed out. Okay. All right. Nice. Okay, so let's think about the time and space complexity for all these things. So for time, so our init is going to be big O of 1. Our set, so I can write these. Our set is going to be big O of 1. Set. Our snap is going to be big O of 1. And this get is the one that takes the while. So get is going to big O of n log, and this is n would be the number of operations you have. So technically, if you did something like, imagine your operation was like this, right? So let's say you have some array, and let's say you have some value like this. Let's say we're at so we're at this dictionary. We're at index 0. We have a list, right? And we have some value, and then we also have our snap here. So let's just say snap, and then we have some value like 0, 0. Now we snap. Then we add another value like whatever. We add a value like 1. Then we snap again. Then we keep adding a value. Let's just say we add a value like 5, and so on. So if we keep snapping and then adding a value, then the most values we can add would be n over 2, right? Because our operations would just be snap, add a value, snap, add a value, snap, add a value, which is big O of n. It's just how many operations you can have. And so this this time for the get is going to be big O of n, where n is the number of calls. So this is number of calls. Because yeah, if you just had a set, snap, whatever, and then you just have one get at the end, that means we would maximize our one index and we'd put everything in there. And so that's the worst case scenario there. Yeah. Okay. Now let's think of the space. So what are we doing? We're saving. So every time we have a set, at most we can save one value. So that's going to be 1. But we can set n times, which is also the number of calls here, plus our initial array is going to be n length as well, right? So if this was actually, so the number of calls here equals the length of the array. So number of calls equals, let's just say L is the length of the array. And so that means that worst case scenario, if we just keep setting and we have the biggest array possible, it would be like this. But because they're equal, this is just number of calls as well, so it's big O of n. Because that would just be big O of 2 times number of calls. Yeah. And the reason we're saving so much space here is because for each set, we're actually only setting one value, where before, like let's say our array was this length, before the brute force would snap the entire array every time. And so that would be this, right? Because we can have n number of calls, and then for each snap, we're saving this whole thing, so that would be n squared. So we got that down to n, and our time complexity is no longer big O of 1, but it's still, this should actually be not number of calls. This should be n log. So this should be number of calls times log number of calls, right? Because it's a binary search. So we did get n squared down to n log n, which is definitely a lot better, and it passes now. And I don't think you can make this be any faster. Yeah, I think the binary search solution is the optimal solution for this. Okay, so that's everything for this problem. Hopefully you liked it. Definitely thought it was an interesting problem. And if you did, please like the video and subscribe to the channel, and I'll see you in the next video. Thanks for watching.